Hi everybody, welcome back to the Feynman technique. Again, today on this channel, I'm going to be trying out this new format that I tried in my last video where we're just going to be solving this integral from scratch. I believe this is going to be solvable with Feynman integration, probably the use of complex numbers, which I've been very fond of using lately. This is an integral I got off the channel Maths 505. I haven't looked at it. I haven't looked at the solution. I will provide a link to his video in the description. I hope the solution doesn't turn out to be too similar. But let's just get started. All right. So we want to use Feynman integration, or at least I do. A big clue that it's going to be effective here is the fact that we have a natural log x in the denominator here, and we have an x here, which is basically just x to the 1. All right, so what we're going to do is we're going to create our function of t to be pretty much this integral, except we are going to say that this is x to the t. Okay, then we can say that f of 0 is going to be equal to 0, because if we plug in 0, we get 1 minus 1 here. So that's equal to 0, and we can also say that f at 1 is going to be equal to our original integral I, and I'll label this I really quick. All right, so next we want to compute f prime of t, and I'm going to denote it f1 of t. So that's going to be the partial with respect to t of this same thing, except we're just taking the partial with respect to t of this. So when we take the partial with respect to t, this whole part's going to cancel out. All right, so we're just going to get a negative there. And then when we take the derivative with respect to t of x to the t, we're going to get back x to the t and then a natural log x, which will cancel that out. And then I'm just going to check to make sure I didn't make any stupid mistakes. I'll just put a little ddt in front of here and make sure those things line up. They do. All right. So now let's go ahead and bring this negative outside and just clean it up by getting rid of these parentheses here. All right. Well, we know by Euler's formula that, well, I'll just show it. If we take e to the I natural log x, this is equal to cosine of natural log x plus I sine natural log x. E to the I natural log x, we can bring this I right inside the natural log as an exponent on x. And then we can, e to the natural log is just whatever's inside the natural log. So that's x to the I. All right, so we can say that the real part of x to the I is just equal to cosine natural log x. So we will represent our f prime of t like this. So f prime of t is now going to be the negative real part of the integral from 0 to 1 times x to the t times x to the I, but that's just x to the t plus I. All right. Well, if we just evaluated this integral right here, just this, that's pretty clearly going to give us negative 1 over t plus 1 plus I. So we need to take the real part of that. Well, if we took, let's multiply the top and the bottom by t plus 1 minus I. All right. So we'll multiply the top and the bottom by t plus 1 minus I. All right, and then this is going to give us t squared, t plus 1 all squared, and then plus 1 in the denominator there. Let's clean this up a little bit. And since we are taking the real part of this, this is going to go away. So we're just left with this. All right, so our f prime of t is actually equal to this. All right, so apparently we could have We didn't need to use complex numbers, I guess. I guess we didn't need to do that. We probably could have done a substitution where x is equal to e to the u and then solved it with integration by parts, probably. But I like doing things this way. I think it's just a lot cooler. So that way I got to use some complex numbers along with Feynman integration in this. All right, so there's our f prime of t. So we don't want f prime of t, we want f of t. All right, I guess I'll solve this from scratch. All right, so we're going to say that f of t, well, that's equal to the integral of f prime of t dt, which is equal to the integral of this thing dt. We will let u equal t plus 1, implying du equals dt. So f of t is now equal to this. I find Desmos to be a really good notepad for mathematics. When I'm just playing around, I use Desmos. It allows you to check your work and make sure you're on the right track. But anyway, okay. So t plus 1 is u. So this is just a u squared. Dt is now du. All right, let's put a 2 in there and put a 1/2 in there. So we can pretty clearly see that this is going to equal negative 1/2 of the natural log of u squared plus 1. But our u is t plus 1. So let's go ahead and just put that right there. All right. So that's our f of t. Oh, and then plus c. All right. So that's f of t. All right. We know from earlier that f of 0 is equal to 0. So we can find our constant of integration. So f of 0 equals 0, which is also equal to this, where t is 0. That's going to make this, let's see. I'm sorry, where t is 1. Oh, no, where t is 0. That's right. Okay. So what did I do? Yeah. So this is 0. This becomes 1 squared. Just 1 plus 1 is 2. So it looks like our c is equal to 1/2, or we'll just say natural log 2 over 2. All right. So our f of t is just equal to this. All right, moment of truth here. Natural log 2 over 2. Yeah, okay. Looks like we got some extra stuff. Looks like our original integral, if you look right here, our original integral wasn't defined. To the left of this little red mark here. But our new f of t is. But it doesn't matter because we're only interested in f of 1, which is definitely within our bounds of where our original integral was defined. So now all we have to do is plug in f of 1, and that's going to give us I, and that is also going to give us this, where t is 1. All right, so let's copy this and compare it to the value of our original integral. Perfect. All right, so that's the answer. Let's clean this up a little bit. Let's see, this is going to become a 4. So we have a 5. We can switch the order here. All right, good. Let's just say that's the natural log of 2 over 5. There we go. So it's natural log of 2/5 over 2. All right, guys, there's another video in this format. I hope, leave a comment if you like this format. I don't know. I like it a little better because you can actually see like my thought process, and maybe if you need something like that to just to get into the mind of somebody that's solving things with Feynman integration, it might be helpful for the videos to be in this format so you can just follow along with not only my steps but my thought process. Anyway, I hope you enjoyed that. We'll see you next time.